When you have a constraint minimization or maximization question, do you always use Lagrange multipliers? Well, in Calculus 3, most of the questions are made for Lagrange multipliers, but sometimes you might see a question where really the Calc 3 method is not necessary. So let me give you an example. Say you wanted the minimum of x squared plus y squared, where you're given that x squared minus y equals to 5. Well, in this case, you would, if you were to use Lagrange multipliers, it's the gradient of f equals to lambda times gradient of g. So you have 2x and 2y. And if you take the gradient of this is 2x and then negative 1. And you can say 1 is the lambda of the other. And sure, you can proceed like this. And it's not really a hard question, but if you look at it in the following way, you see that this is not actually needed. See, if x squared is equal to 5 plus y by adding y both sides, and if you can replace x squared by 5 plus y, so let's say y, x squared is 5 plus y, so 5 plus y squared, then this function, after replacing x squared by 5 plus y, just becomes a single variable function. We know very well how to minimize this or maximize this. You just set the derivative equal to 0. You find a critical number like that, right? So you get 1 plus 2y equals to 0, so that y must be negative 1/2. You just have to make sure that x is still defined. If you plug in y equals to negative 1/2, x squared is 4.5, so yeah, x is plus or minus square root of 4.5. So there's no problem there. And therefore, there you have it. That's the minimum. So let's see. So if I plug it in here, I get that x squared must be 5 plus negative 1/2, which is 9 over 2, because 5 is 10 over 2. And then y squared would be, if you squared negative 1/2, would be 1/4, right? So x squared plus y squared would be 9 over 2 plus 1/4, which is 9 would be 18 over 4, so 19 over 4. So it works like magic. Of course, you probably need to do some more analysis to show that this is a parabola that's opening up, so the critical number should be the minimum, so you do have the minimum. But the point is, sometimes it's easier to do it using the Calculus 1 method. Alright, so let me show you another question where this type of thinking applies. This is a question where you're again given a two variable function, but this time you're trying to find the max and min on a closed domain which has an interior. So let's first think about what this means. Absolute value of x less or equal to 1 means x has to be less than 1. But you can't be like negative 2, because the absolute value of negative 2 would be positive 2, and it's not less than 1. So it can go to the negative side, but the most you can go is negative 1. So absolute value of x less or equal to 1 means x must be between 1 and negative 1. The same thing applies for y. Y absolute value being less or equals to 1 and negative 1 means y must be like this. But then you're collecting all the points whose x and y values satisfy this. So it can be any point here, because if you have x comma y, sure enough, your x coordinate will be between negative 1 and 1, and your y coordinate will be between negative 1 and 1 also. So if you think about all these other points which will have both x and y being between negative 1 and 1, you end up with the following domain, which is actually a square. Mine looks more like a rectangle, but I was supposed to be drawing a square. Square of side length 2, and you have this boundary. Okay, so how do you find the maximum or minimum of a function defined on a domain like this? Well, you have to think of it in two cases. One is, what if, so case 1, if max min is on, or inside, or it's in the interior. And case 2 is if max or min is on the boundary. Okay. Alright, so max min is inside and max min is on the boundary. And the reason I distinguish between these two is because inside it really doesn't have any constraint. It could be, I mean, being inside is sort of a constraint, but it's not like a equation that it has to satisfy. All it needs is that the values of x and y should be strictly less than 1. Absolute value of x and y should be strictly less than 1 to be inside this square. Whereas if you're on the boundary, that's really a constrained optimization question, because for example, if it's on this boundary, what is this equation? That's x equals to 1, right? This equation would be x equals to -1. This one here will be y equals to +1, and this would be y equals to -1. So these are equations. So at the boundary, this function x and y better satisfies some equation, which means it's a constraint. In those cases, we were told that you have to use Lagrange multipliers. Okay, so let's do this first. How do you get the local max or local minimum inside? Well, whenever you have a minimum or maximum, we know that it has to be a critical point, meaning that the gradient must be 0. Gradient of f, if you compute it, it's 2x plus, you first have to differentiate by x, treating y as a constant, so these become 0. Differentiating x squared y just gives you x squared. Then differentiating this by y treats x squared as constant, so that goes away. You get 2y, and then differentiating x squared y by y, you just get x squared, and 1 is a constant, so it differentiates to 0 again. Okay, now we set that equals to 0, so either 2x plus x squared, sorry, this should have been 2xy. I made a mistake. Okay, so either 2x plus 2xy has to be 0, or 2y plus x squared must be 0. Now this thing can be factored by 2x. If you factor this by 2x, it's 2x times 1 plus 2y, 1 plus y equal to 0. So either x is 0 or y is -1. So you have two cases. If x is 0, 0 times anything is 0, so it's going to satisfy this. If y is -1, it will again satisfy this. And we know that's the only possibility, because if two things multiply to 0, either one has to be 0. So we have those two cases. And then we have to track these cases down again. So case 1 and case 2. When x is 0, we get, you plug in 0 here, 2y plus 0 squared is 0, so you get y as 0. Now case 2, if y is -1, you can plug it in here, you get -2 plus x squared equal to 0, so x squared must be 2, so you get x equals to plus minus radical 2. And therefore we get points 0, 0, or plus or minus square root of 2, -1. However, actually this is my second time recording this, because in the first try I made a couple of errors, and one of the errors was thinking of this as one of the possible location for max min, but that's not true because -1 means you're here. And radical 2 is actually bigger than 1.4, right? It's bigger than 1, so actually -1, so radical 2 comma -1 is somewhere here. Negative radical 2 comma -1 is somewhere here, so that actually shouldn't be part of the consideration. It's outside the interior. We need the points to be interior, but this is outside this domain, so this is not considered at all. So the only thing that we have to consider for case 1 is when we have 0, 0. Okay. Now, then for the other case, when max or min may happen at the boundary, you might think, well, it's say x equals to 1. That's a constraint. Gradient of x would be, if you differentiate by x, it's 1, but if you differentiate by y, it's 0. So you might say, here's our gradient. This should be some lambda times this number. So that seems to be a good approach in most cases, but in this case, because x is simply 1, this is such a nice thing to just plug in, just like how we solve the first equation, right? You just plug in 1, and what does that mean? If x is 1, then you get 1 plus y squared, and that's also 1, y squared plus y plus 2. And that means that if I have y equals to -1/2, if you differentiate this and set it equal to 0, you get y equals to -1/2, and therefore you get the so what you get is the minimum value would be when y is -1/2, which is this will be 1/4 minus 1/2, so that's 1.5 minus plus a quarter, so 1.75 is what we would get. So that will be the minimum. Also, because y is between -1 and 1, if you plug in 1 or -1, if you plug in 1, you get 4. And if you plug in 1 comma -1, if the y value is -1, you get 1 plus 2, 3 minus, you just get 2. Okay, so these are the points. Now, if you just use the Lagrange multiplier, these two endpoints will kind of be invisible. Actually, and that's another reason why you don't want to use Lagrange multipliers in this case when you have like corners like this. If you do have to use Lagrange multiplier, then these endpoints has to be considered separately. So it's really case 1, 2, and 3. One for the interior, the secondly on the edges, and then for the vertices. So it's actually really confusing if you try to use Lagrange multiplier here. All right, so let's continue. What about when you're on this side, x equals to -1? Well, that's you get again 1, but this one will be, because x is squared, it's not going to do anything. You're going to get +1, so you again get the same exact equation. All right. So in this case, you would get again at y equals to -1/2, f would be 1.75, and at -1, 1, you're going to get 4, f -1, -1, you're going to get 2. Okay, now let's move on to y equals to 1. fx, 1 would give you, if you plug in 1 here, you get x squared plus 1 plus x squared plus 1. So 2x squared plus 2. Well, what is that? That's a problem that looks like that, right? So its minimum is when x is 0. So f01 would give you 2 as the minimum on this top part here. And then the corners are when you have f11 or -11, but they are both considered already, so I don't have to consider it now. And then finally, f of x -1. Well, that's a little strange. If you plug in -1 into y, you get -1 squared is +1 minus x squared plus 1. So these cancel, and it's always 2. Okay, and then I forgot to actually calculate at 0, 0. So what is f00? 0? If you plug in 0, 0, 0, 0, it's just 1, right? So you get that, okay? So while doing this, I figured out all the candidates for minimum or maximum. If it's inside the domain, it must happen at 0, 0. Maximum or minimum, if it happens inside the domain, it has to happen at 0, 0. If it happens somewhere on this boundary, then there's 4 cases, 1, 2, 3, 4, and I tried to look for each individual cases and said, oh, you can have like 1.75 at some places, or it could be 2 or 4. These are the possibilities. But among these, since these are the only possible places where you can have a max or min, it's a competition just among these numbers. So I have so many different places, but where's my maximum value? Well, I see the maximum value being, let's see, I see a maximum value here. That's a this is a maximum value. 4 is a maximum value, right? Yeah. And the minimum value is this one, okay? So I would say the answer to this is max value of 4 at 1, 1 and -1, 1, okay? And the minimum value of 1 at 0, 0, okay? So that would be the answer for this. So it's, if you have done the one for the case where the domain is a circle, that's a classic question for using Lagrange multiplier at the boundary, because this way of approach is very complicated if you do it that way. But for this question, contrary to what you have been doing for a lot of constrained equations, it's actually better just to plug in these values and try to see if you can just use the calculus 1 method.